Now we turn to looking at spanning trees. A spanning tree is a network in which all the nodes are connected and there are no cycles. Spanning trees are used in designing circuit boards for computers, laying cables, air conditioning rooms, etc. Perhaps the most important point here for a spanning tree is that there are no cycles. In the networks I've shown here, the first two are spanning trees, but the other two are not, and the question is why. In the first couple, you can see here that all of the nodes are connected, but there's no way for me to make a cycle or a loop. Same is true for the second example. There's no way I can make a loop there. In the third one though, you can see that I do have a cycle here. In other words, I can go around in a loop, which means this is not an example of a spanning tree. In the last one, you can see that I have an arc which is not connected in any way to the others. So this cannot be a spanning tree either. The question now is, how can I turn these diagrams into spanning trees? In the first case, I would actually need to delete one of the arcs. So for example, I could delete PT and then all of the other arcs are connected. In the last one, I would need to connect this arc to the rest of the diagram in some way. Any of these lines will do the job. So how do we find the minimum spanning tree? A minimum spanning tree involves finding a spanning tree so that distance, cost or time is kept to a minimum, the lowest possible number. Here we use Kruskal's algorithm. You start by highlighting the arc with the smallest distance, cost or time, etc. and continue to highlight the arc with the next smallest. And you keep going until you have one less arc than the total number of nodes in your diagram. Now an example will make it all clear. These are kind of fun. Unlike finding the shortest path, there's no starting point. We're simply looking for the smallest number on the diagram, which is this one. Now we look for the next smallest. That looks like a 12. The next smallest from there is a 15, and then a 17. The next smallest number is a 20, and then a 21. And now I get my first little problem. The next smallest number is a 23. But if I select this one, I make myself a cycle, which I'm not allowed to have. What about this one? Once again, that will make a cycle. So I can't have that one either. So I can't highlight the 23s. For the same reason I can't highlight the 25s, because that would also give me a cycle. So the next highest number is a 27. And now you can see that I have all of the nodes connected. In this network there are 8 nodes, and if you count the arcs that we've highlighted, you'll find there's 7. And that satisfies the final condition that the number of arcs should be one less than the total number of nodes. And that's a good way to check that you have completed the spanning tree. What about this one? The diagram shows the positions of tents on a campsite with the distances between them in meters. And we have to link all of the tents by paths so that the total length of pathway is minimized. Okay, can you remember the first step? We look for the smallest number, and that's a 25. The next smallest number is a 40. Now there's more than one 40, so I will highlight both of them, being careful to make sure that I'm not creating any cycles. The next smallest number is a 45, followed by a 50. I only have 2 nodes remaining to connect, the A and the B. My next smallest number is the 60, which connects A. And then finally, to connect B, I have a choice of 70, 80 or 100. So naturally, I'm going to choose 70. So the number of arcs is indeed one less than the number of nodes, which enables me to conclude that I've done the problem correctly.